In this video, I'll demonstrate Task Systems, our component-based plant modelling toolkit. Once I've already simulated a building and found the heating and cooling loads for the different zones across my model, I can use Task Systems to model the HVAC circuits and the plant circuits, such as the heating, cooling, boilers and chillers, to determine the overall energy consumption and cost and unmet hours of my model. To create a new system, I simply drag and drop components from this built-in library, dropping these onto our schematic. And connect them together to represent the air paths that flow between the different components. Here I'm modelling a simple extract and supply fan coil system. Where I have a supply fan with a heating and cooling coil, an extract fan, a heat exchanger in my air handling unit, and within the zone itself a fan coil unit which will do terminal heating, cooling and recirculation of air. Once I've created the schematic layout, I can then enter component information for each of these components. For example, the efficiency of my heat exchanger, and I can choose how to control my heating and cooling coils. So these will be controlled to regulate the temperature of the air at this point in the circuit. I'm just going to enter the remaining component information, and then I'll show you how we can simulate the circuit and look at the results. Now that I've entered the component data, let's take a look at the heating coil. And I've set this up to be sized based on the results of a steady state design day. And the heating coil is going to heat the air at this part of the circuit to 20 degrees. The cooling coil will cool the air to 24 degrees and is sized based on the summertime period. That's days 121 to 273. Now I'm ready to add zones from my building to this circuit. If I look at this errors list, Systems tells me what I still need to do before I can simulate the building. And it says that I need to apply a zone to this component here. So I can go to my already imported building and simply drag and drop zones onto my circuit. Now I'm ready to simulate this system. As you can see, the system simulation for a single zone is extremely quick. Looking at day 2, the second day of the year, and from 9 AM till 10 AM in the morning, I can start to interrogate individual parts of this HVAC circuit. The heat exchanger is recovering heat from the extract stream, and the air is being cooled down from 20 to 10 degrees to heat up the supply air from 6 to 16 degrees, which is reducing the load on the heating coil. As I've assigned a heat gain factor to my fan of 0.925, I can see that the temperature of the air passing through the fan increases slightly. And I can then look at the electrical load assigned to the terminal component on the zone. I can add multiple zones on the same circuit by adding a damper and splitting the airstream between these different zone components. So let's do that next. You see how easy it is to add components to an existing system. If I now group this zone and damper component together, I can simply drag an entire set of zones onto that part of the circuit, and it creates 21 copies to fit the 21 zones in that set, with each subgroup containing a different zone. Here's the simulation run for all 21 zones. Now I can look at the individual fan coil unit for each of the zones and view a graph of the load across the day. You see that the different zones have different loads at the terminal units, but I also have the total sensible load for the heating coil in the AHU. Most of the work in the winter is being done by the sensible heat exchanger. Once I've created a system, I can save it by grouping the entire system and adding it to my library. Now I can reuse this system again in other projects simply by dragging and dropping from the library. If I want to model a more complex system, then the project wizard can help me to set that up initially, and then I can make changes to it. I'll run the project wizard and choose to create a new system for my building. First, I choose the zones from my building that I want to apply to the system, and I can have multiple different systems here and mix and match zones between them. Then I choose a system from a drop-down list. Here I've selected a CAV system with a constant supply volume of air and reheat within each of the zones. Each of the heating coils and radiator components can be assigned to heating circuits, and then I can edit the information for the boiler, including its efficiency and fuel type. TAS allows me to model as many different boilers as I want, with different fuel types, and these can either run in parallel or in serial. Once I've entered the information for each of the boilers, including all of its part load efficiencies, TAS will show a graph of the overall efficiency for all of my boilers. I set up the cooling circuit in the same way. This time I'll assign an electric heat pump with a COP of 4.5, and finally the domestic hot water services. And again I'll set these up to just direct electric heating. After I've set up the basic systems, I can add renewable energies, such as PV panels and wind turbines. To add a PV panel, I simply apply surfaces from my model for which I've saved the amount of solar gain absorbed. I have the option then to edit the efficiency of the panel if I wish. But at each stage, TAS Systems is creating default values so that I can proceed through the project wizard quickly and then add more detail later on if I wish. I will also add a wind turbine, And again, this comes with a built-in efficiency curve, which I can customize. Finally, I apply the remaining components to fuel sources. My renewables will be creating grid-displaced electricity, which will effectively offset CO2 from the natural gas and the grid-supplied electricity. Then, all the components on my circuit need to be sized before the simulation can run. My building has a heating design day, which is a steady state simulation which I'll use to size the components of my heating circuits. To size the cooling circuit, I'll create a new design condition, just including the summertime months. Once I've entered that information, Task can generate a new system based on my inputs. So here I have a CAV circuit, again with a heat exchanger, and now a mixing box which can be temperature optimized to vary the flow of air through my circuit. And my cooling coil and heating coil will be sized based on the peak demand of all of the 21 zones I've assigned to the circuit, but they have an individual reheat radiator for each zone. Even with a circuit this complex and with 21 zones assigned, the simulation is still very quick. As well as interrogating individual parts of the circuit, I can also look at the results from my entire building broken down by end use, or in more detailed view, the load on all of the heating and cooling coils, the demand on my boilers and chillers, and the energy consumption of those chillers. And I can convert this to a weekly or daily or hourly view as well. I can see the fuel types used in the building. Here I'm consuming natural gas and grid supplied electricity. In the summer, where I need to do less heating, I'm using less natural gas. And there's also a chart showing the amount of electricity generated by my PV panels and my wind turbines. If I edit the properties of the fuel sources for my building, I can also look at the amount of carbon dioxide emitted and the cost of using this electricity and gas. So for the grid supplied electricity, there is an assumed CO2 factor which I can modify, and a tariff which is currently set to 13 pence per kilowatt hour. I will add an off-peak rate based on the occupancy schedule of my building, and then in the results I can see the overall amount of carbon consumed and the cost of that energy, with the grid displaced electricity offsetting that cost. All of these charts can then be exported either in their raw text format or as one of a number of formats of images.